So this is class number 9 of cryptography and network security. In this class, I will give you some revision on the theories of numbers. Okay, so how it is applied in cryptography and cryptographic algorithms. Already everything is discussed to you, and today just I am reminding you what are the algorithms and theorems which we are going to use in the coming classes. Right? So that is introduction to number theory. The basics of number theory, we will use some of them. So first one is modulo arithmetic. It is important for the cryptographic and network security classes. Addition and additive inverse are easy. Multiplicative inverse doesn't always exist because we have to use extended Euclidean algorithm for that. You know, if there is only GCD of two numbers is 1, then only multiplicative inverse of that number is present in that colloquial. Otherwise, multiplicative inverse is not available. Okay. So other than 1, there is no multiplicative. So multiplicative inverse is not always exist. Properties of prime number. A prime number is divisible only by itself and 1. Determining the primality is not all that easy, you know. Okay, so for small numbers it might be easy, but in case of very large prime numbers, to test whether it is prime or not, it is a very difficult part. A multi-word arithmetic, additional methods, Chinese remainder theorem of finding inverse in the finite field. Modified extended Euclid's algorithm applies also here. Okay, so the number theory theorems can be useful, very useful for the cryptographic algorithms. Already we have discussed. That's why we are going to discuss all this. Okay, so in a public key encryption system, that is private key cryptographic algorithm, RSA algorithm or elliptical curve algorithm that will be used. The Diffie-Hellman key sharing, key exchange algorithm. And this is very important. Chinese remainder theorem and generation of testing of large prime numbers, useful in all of the above. Okay, so that's why the theory of number system is very important for not only for cryptography but for all the other subjects. This is the basis of any research. It is applicable. Okay, so but specifically the number theories or theorems are used in the cryptographic algorithms, and these are some examples. Okay, the prime factorization theorem. A prime is a number that is divisible only by itself and 1. Any number can be factored uniquely into a product of primes to some power. For example, here, and that is 1100. So 2 to the power 2 is 4 into 25 into 1, 11. So that is, so here it is written 2 to the power 2 into 5 to the power 2 into 11 to the power 1. So relatively prime, that means already we have discussed in the extended Euclidean algorithm. That means if the GCD of two algorithms, two numbers are 1, then it is known as the A and B are relatively prime. Okay. So next, useful theorems involving in a to the power x mod n will discuss in the next slides. So the first one is Fermat's theorem. Fermat's theorem is telling a to the power p minus 1 is equal to 1 mod phi. P doesn't divide say. Euler's phi function. Phi n is number of numbers less than n and relatively prime to n. So relative phi n is relatively prime. Phi n is relatively prime to n and less than n. So easily found if factorization is known. Euler's theorem. This is Euler's phi function and this is Euler's theorem. The first calculate the phi n, Euler's phi function, which is less than n number of elements less than n and relatively prime to n. Okay, and then a to the power phi n is equal to 1 mod n, reduces the Fermat's for n prime. Okay, Miller-Levin test, that is based on inverse of Fermat's theorem. N is not prime if on 1 k1 mod n is there. First exponentiation, convert x to binary. For example, x to the power 8 is x square 3 times. Okay, so prime numbers, the prime numbers only have divisors, so 1 and self. Okay, they cannot be written as product of other numbers. Note, 1 is prime but is generally not of interest. The prime numbers 2, 3, 5, 7 are prime, 4, 6, 8, 9, 10 are not prime. So already you know, prime numbers are central to number theory. List of prime numbers less than 200 is given, so there is 2, 3 up to 199. So that you know, this is not new to you. So all of us have discussed this. We have written many programs to calculate the prime numbers. To factor a number, n is to write it as product of other numbers. We can write n is equal to a into b into c. Note that factoring a number is relatively hard compared to multiplying the factors together to generate that number. The prime factorization of a number n is when it is written as a product of primes. 91, that is the prime factorization. When the product of primes, then it is known as prime factorization. 7 into 13, so 7 is a prime number, 13 is another prime number, so that is 31. So similarly, that is prime factorization. 2 is a prime number, 3 is a prime number, and 5 is a prime number, so that is the prime factorization. Relatively prime, already we have discussed in the previous classes, and the class number 7, 8, both in both the classes we have discussed about the relatively prime number. When the GCD is equal to GCD of two numbers are equal to 1, then it is known as relatively prime. Then A and B, suppose GCD of A and B are 1 is 1, so then A and B are relatively prime if have no common divisor apart from 1. Okay, and example 8, examples, that is 8 and 15 are also relatively prime, since the factors of 8 are 1, 2, 4, 8 and 15 are 1, 3, 5. So they are also 8 and 15 also relatively prime. Conversely, can determine the greatest common divisor by comparing their prime factorizations and using the least power. Definitely is. Okay. So here, so by comparing their prime factorizations and using the least powers. So that is by using, we can calculate the GCD. So here come to the Fermat's theorem. The Fermat theorem is that a to the power p minus 1 is equal to 1 mod p, where p is a prime number and GCD of a and p is 1. Right. So remember this, we'll use it in the different purposes. So in RSA algorithm, in the Diffie-Hellman algorithm, and other public key encryption systems. Okay, so a to the power p minus 1 is equal to 1 mod p, where p is a prime number and GCD and a and p both are relatively prime. A and p are relatively prime, also known as Fermat's little theorem. So also a to the power p is equal to p mod, so that is also known as Fermat's little, useful in public key and primality testing. Also it is affirmative but not negative, a test for primality. So here we have got 2 points here. A to the power p minus 1 is equal to 1 mod p, and a to the power p is equal to p mod e, a little theorem. Okay, so these two. Next, Euler's quotient function phi n. When doing arithmetic modulo n, complete set of residues 0 to n minus 1. A reduced set of residues is those numbers residues which are relatively prime to n. For example, n is equal to 10. Complete set of residues is 0 to 9. And reduced set residues to 1, 3, 7, 9. Number of elements in reduced set of residues is called Euler's quotient function phi n. When doing arithmetic modulo n, so that is known as reduced set of residues is those numbers which are relatively prime to n. Okay? Relatively prime to n, only that number, those numbers. Okay, so n is 10, so less than 10, 0 to 9, relatively prime to 10, 1 is relatively prime to 10, 3 is relatively, that means 10, 1, GCD is equal to 1. Then GCD of 10, 3 is equal to 1. So only we will select those numbers whose GCD with 10 is 1. So out of this, so that is the Euler's quotient function. Okay, this is very useful. Euler's quotient function phi n, let's say. To compute phi n, need to count number of residues to be excluded. In general, need prime factorization, but for p prime, phi p is equal to p minus 1. For p dot q prime, phi pq is p minus 1 and q minus 1. So for example here, phi 37, that means here, phi 37, that means here, that is p minus 1. So 37 minus 1, that is 36. Okay. Phi 21, phi 21 is, that is a factor 7 into 3. So 7 minus 1 is 6. Oh, that is 12. That means here phi pq. So multiplication of two primes. Multiplication where p and q are prime numbers. So two primes. So then p minus 1 into q minus 1. So that is 7 minus 1 into 3 minus 1. So that is 6 into 2. Okay. So Euler's theorem, a generalization of Fermat's theorem. So a to the power phi n is 1 mod n for any a n where GCD of a of n is 1. Then a and n are relatively prime. Are relatively prime. So suppose here, for example, a is 3, n is 10, so phi 10 is equal to 4. Hence, 3 to the power 4 is equal to 81. 3 to the power phi n is 4, phi 10 is 4. So 3 to 3, a is 3. So 3 to the power 4 is 81. That is equal to 1 mod 10. Okay. So phi of a to the power phi of n is 1 mod n for any a n where that is relatively prime. So here a is 3, n is 10, so phi of 10. So here 3 to the power 4 is equal to 1 mod 10. So 1 mod 10 is 1. So 3 to the power 4 is equal to 81. 81 is also. So a is 2, n is 11. So 1024, that is also 1 mod 11. So you will find that. Okay. Primality testing. Often need to find a very large number, traditionally achieved using trial division, that is divide by all numbers, prime numbers, in turn less than the square root of that number. Only once for small numbers. Alternatively, can use statistical primality test based on properties of primes, for which all prime numbers satisfy property. But some composite numbers called pseudo primes also satisfying the properties. So that is known as shadow primes. Can use a slower deterministic primality test. Miller-Robin algorithm. A test based on Fermat's theorem. Algorithm is find integers k, q, k is more than 0. Q word so that n minus 1 is 2 to the power k, q. So that is based on the Fermat's theorem. So find the integers which is more than q so that this 2 to the k n minus 1 is equal to 2 to the k into q. Select the random number generator. If a to the power q mod n is 1, then return may be a prime number. Otherwise, repeat this process till the result arrives. Okay. Then probability considerations. If Miller-Robin returns composite, the number is definitely not prime. Otherwise, it is a prime number or a shadow prime number. Chance it detects a shadow prime number is chance it to detect a shadow prime number is 1 by 4, less than 1 by 4, very rare. Hence, if a repeat test with different random, then chance n is prime after t test is, that is prime number, n prime number, that is 1 minus 4 to the power e. Okay, prime distribution. The prime number theorem states that the primes occur roughly every natural logarithm n integers, but can immediately ignore the evens. So in practice, need only test 0.5 log n numbers of size n to locate a prime number. Note this is only the average. Sometimes the prime are close together. Other times are quite far apart. Chinese remainder theorem used to speed up the modulo computations. It is working modulo a product of numbers. Mod m is m1 dot m2 dot up to mk. Chinese remainder theorem let us work in each moduli mi separately. So that is mod m is multiple m1 m2 dot. Since computational cost is proportional to size, this is faster than working in the full modulus m. Okay, so can implement CRT and several Chinese remainder theorem in several ways. To compute A mod m, first compute all AI, that is A mod mi separately. Determine the constant Ci below, where mi is equal to mi by mi. Then combine the result to get the answer. Okay, so primitive roots from Euler's theorem of a to the phi n mod n is equal to 1. Consider a to the mod is equal to 1 mod n. GCD of a comma m is equal to 1 must exist for m is equal to phi n, but maybe smaller one once power reach m cycle will repeat. If the smallest m is phi n, then a is called primitive root. If p is prime, then successive powers of a generate the group mod p. These are useful but relatively hard to find. Okay, so these are the discrete logarithms that is very useful here. So these theorems already you have discussed in discrete structures, so we are going to use in cryptographic structures, cryptographic algorithms. Okay, thank you very much for attending the class, and actually the real cryptographic chapter will start from the next class. So next class will start with DES algorithm, where you will able to know how the advanced cryptographic cipher algorithms are working, and that those are purely based on the number theory. Thank you.